Nope. Probably Thursday. I'm like halfway done. Grading them.
What's it looking like?
I think it'll be a little bit better than the first exam in terms of average. What is so sorry inside for me.
Actually, would have been what he were. I, you know, like I got some. I almost like half of it. Right. Like folders, so banana. Good. Yeah, I was gonna like. Yeah. Dr. Grant.
What's up?
How's the so far progress looking like, the average?
I think it's gonna be a little bit better than the first exam. I'm about halfway done grading them, so I'll have them done by Thursday.
100%?
I haven't gone to your guys' yet.
So you did really bad.
100% half.
100% divided by 2?
Yes.
Still 50 out of 50.
That's a bar.
All right, it's 1 o'clock. Let's get started. All right, good afternoon, everyone. How's everyone doing today?
Yeah, how you doing?
Good, good. We are winding down the semester, so we are week 14. We got this week, next week, and then one more week after that. So what's up?
We just call it.
No, we got to do radiation. We can't do heat transfer without radiation. So Okay, so plan for today is, well, plan for this week is we have, going to finish up this set of lecture notes on radiation. So this lecture notes is kind of introducing just the concepts of radiation. And then next week is when we're going to do a little bit more heavy into the calculations. So I do have one more homework assignment for you guys. That's probably going to be due probably very last thing of the last week, based on all this radiation stuff. I probably won't assign it just yet. I think you guys need a little bit of a break after the midterm. But probably look for it to be assigned probably early next week. And then it's going to be due end of week 16. Okay. Because right now, we're still going over just the conceptual stuff, so it's a bit early. All right, and so if you weren't here at the very beginning of class, I'm about halfway done grading your guys' exams, so I'll have them done by Thursday. So far it's looking good. So far I think the average will probably be a little bit higher than the first exam. So I think first exam average was 37 out of 50. I think this will probably be a little bit higher than that. At least that's the sense that I'm getting. But we'll see what happens when I grade the rest of them. So I might try to grind it out tonight actually, because tomorrow I'm gonna be pretty busy with meetings and stuff. So your grade will either be posted tonight or probably sometime tomorrow, maybe late tomorrow afternoon. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and pick up where we left off last Tuesday. All right. So it's been a little bit of time. So we kind of had something on Thursday, the midterm that kind of broke up this lecture series. So let's do a little bit of review. So this last unit that we're going over, right before we end the semester is all about radiation heat transfer. Okay. So we're in kind of the very early stage of just introducing the concept of radiation and building up kind of our intuition before we really start to do any of the calculations. Okay. So the idea with radiation, or the main thing with radiation, remember, is that radiation is the third mode or the third form of heat transfer outside of conduction and convection. Okay. Right. So, this whole class is kind of broken down, or, it's kind of organized around those three different modes of heat transfer. So first unit, for the first midterm, we went over primarily conduction. Second midterm, the one you guys just finished taking, was convection. And then this last topic is radiation. Okay. Now, radiation is the kind of the odd one out in terms of the modes of heat transfer, because the way it works is very different compared to conduction and convection. Okay. And so what we said last time was radiation was essentially the transfer of thermal energy via electromagnetic waves. So it's not molecular transfer of heat, which is what conduction and convection was. Radiation, for all intents and purposes, you can consider that to be transfer of energy through light. Okay. Now, the most important consequence of this is that because radiation doesn't require any kind of molecules or any kind of matter, radiation heat transfer can occur within a vacuum where there's no matter present. Okay. And that's really unique because there are a lot of applications for this that are, where, heat transfer has to occur, but there's no matter or anything in between, right? So remember the primary example that we went over last time was solar energy, right? So, all the energy that the sun is giving off at any given time, the only way for solar energy to reach Earth is through radiation. There's no, or I would say very little matter in space through which, heat can transfer, okay? All right. And so this kind of feeds into its applications as well. So because radiation doesn't require any medium or any kind of matter to transfer, you know, most of the time you're going to be concerned about radiation in space applications. Okay. And the reason for this is because, you know, when you're talking about heat transfer on planet Earth, usually there's some kind of matter or atmosphere or air. So usually when you're quantifying the amount of heat transfer that is occurring, usually conduction and convection are much higher in magnitude than radiation. Right. So for most of your applications, unless you're working in an aerospace company, you're designing a satellite, most of the time you're going to be ignoring radiation. And that's part of the reason why we kind of save until last in the class. But you know, for the times where it is relevant, it is important to consider because there's literally no other way to cool down your satellite than to design it with radiation in mind. Okay. There are a few applications on Earth here where radiation is significant. But those are kind of few and far between. And, you know, I think we talked about a couple of examples last time, but, you know, we'll kind of reintroduce those as those come up. Okay. Okay. So that's basically a summary of what we talked about last Tuesday, where we just kind of introduced this idea of radiation. We talked about how it actually propagates, and we talked about its applications. And so today we're actually going to start to get into, you know, how do we actually do computations and some of the modeling for this. Yeah, question.
That's really helpful. What's the difference between like the heat transfer radiation and like nuclear radiation?
Yeah. So it's used in the same term is used, but they do describe different things. So that kind of radiation is well, they're similar in terms of how they travel through space. That's probably why we use the same terminology, but the physical effects of what happens are very, very different. So this radiation, we're talking just purely on heat transfer thermal applications. No, you know, yeah, no nuclear radiation or X-rays or things like that. Yeah. Mm-hmm. All right. Any other questions before we move on? Okay. All right. So the first new topic for today is this idea of radiation intensity. Okay. All right. So intensity is a concept that we use to describe, well, you know, to put it in you know, conversational terms, you know, how intense the radiation is. I think it's probably easier to explain with a picture, right? Okay. So generally the geometric model that we use for radiation is that, you know, what we said last time was that every object that's at a non-zero temperature is going to give off radiation, right? Which is essentially every single object. All right, so let's start with that. So we'll say all objects emit radiation. Okay. And, you know, ignoring any kind of, you know, optical properties on the surface. So, you know, depending on the color of the surface or, you know, the roughness of the surface, you know, there is some room for heterogeneity. But for now, we're going to assume that the object emits radiation equally in all directions without any preference for direction. Okay. What we're going to say is that all objects emit radiations in all directions equally. Okay. All right. So if you have kind of an arbitrary potato-looking object here, we'll say that it is at a temperature Ts. Okay, or at least the surface is at a temperature Ts. Right. And what we can say is that this object is going to be giving off radiation in all directions equally. Okay. Okay. Now, last time we went over an equation that computes the total amount of heat flux coming off this object. Okay. Right, so we defined that variable as E. Okay. And so this is the total emissive power. Right. So emissive power, that's basically the term that we use for, the total amount of heat flux radiation coming off this object. Okay. We said this is equal to epsilon, which is the emissivity of the object, times the Boltzmann constant sigma, times the temperature of the object raised to the fourth power. Okay. Let me just label these again, just because it's been a while. So this is emissivity. This right here is the Boltzmann constant. Okay. And then TS is just the surface temperature. Okay. Question, yes.
So there's two different names for E.
Well, E, we give it the name emissive power for radiation, but the way that we interpret it for heat transfer is that it's essentially a heat flux.
Because I think last time I just wanted to make sure that I got it down correctly. You said that it was spectral heat flux as well, or?
Yeah, so spectral heat flux, emissive power, same thing.
Okay,
Yeah.
thank you.
Mhm. All right, so the units for this is watts per meter square. Okay, so this formula here tells us how much radiation is coming off this object in total, right? And this emissive power is essentially going to be spread out equally in all directions. Okay, now let's put another object here. So let's put another object that is going to catch some of this radiation. Okay. So when we put another object, so let me draw our potato again. Okay. Right. So we drew our potato, our radiating potato here, right? If we draw another surface, and we'll make it simple, we'll make it like a disc. Okay. All right, so let me fill it in just to make sure that it's, you guys know it's a solid object, it's not a ring. Okay. All right, so what's going to happen is that, this surface is going to catch some of that radiation, right? Okay. So some of the radiation coming off our potato will hit our disc here, right? But because this disc is not fully encapsulating this potato, there's also going to be a lot of radiation that goes around it too, that's going to miss, right? And so if we extend some of these lines, right? So this line right here was going to hit it, right? So this line will just barely miss it. I probably should have drew more lines here, right? Right. So there will be a mix of, some radiation that's going to hit it and some radiation that's going to miss, okay? Okay, and so if we want to ask the question of, how much radiation is this second object, how much is it receiving from the first one? Well, it's a bit complicated because we can't just simply say, right? We cannot just simply say that this object is taking over this entire emissive power because a lot of it is just simply just going to miss the object. Let me zoom out, you can kind of see both. Okay. Okay, so all we've done so far is talk about how much emissive power is coming off the object, but we haven't really said anything about how much of that is actually going to hit another object that's in its general vicinity. Okay, we did do one example last week, so we did do one example of a pipe in a large room, but that one we kind of did a simplified geometry because we kind of assumed that all the radiation that comes off that pipe is going to be absorbed by the room, and everything that the room gives off is going to be absorbed by the object. But that was a special case where, the object completely encapsulates the room completely encapsulates the object that we're looking at. Most situations are not going to be like this, especially if you're going to be out there in space. Okay. Okay, so what you're going to see is that there's a huge, geometrical aspect to radiation that, is really going to complicate a lot of our calculations. Okay. Okay. Any questions on this so far? Okay. All right. So we need to basically, come up with a way to describe the geometry of the situation so we can, really compute, radiation heat transfer exchange between objects. Okay, so let's introduce a new geometrical concept. So probably you guys have not gone over this before. And so that's the idea of a solid angle. Okay. So a solid angle, you can think of it as kind of like a three-dimensional extrapolation of the concept of a regular angle. Okay. Okay. So let me introduce it like this. So let's talk about kind of the two-dimensional version with the regular angle, and then we'll talk about its three-dimensional version right after that. Okay. Okay. So in 2D, right? So angles is something that you guys have used a lot, right? In a lot of other classes, right? So in 2D, the concept, one way to look at an angle is you can look at the angle as as kind of a way to talk about the segment of a circle that gets subtended by an arc. Okay. Okay. So let's say let's draw an angle here. Right. So most time, we think of angles that look like this, right? So an angle is just kind of the measure of the orientation between two different, line segments, right? So we draw one line segment, another line segment, and then the angle is the way to describe, how different their directions are. Okay. Another way to look at the angle is that, if we consider this, these two line segments as a slice of a pie, right? Where we call, this section in red right here, right? We'll call this an arc. Okay. Right. Where if these two line segments have the same length, so let's say they're both have length r, right? Right. We can say that this arc represents a part of a bigger circle, right? So if we kind of continue on with this, right? We can draw a circle. Imagine that's a perfect circle. I just ran out of room on the left side there. Okay, right? Right. So that arc is part of this bigger circle right there, and this angle describes, how much of this circle that arc kind of makes up. Right. So it's a non-dimensional way to describe, how much this arc takes up, for this given angle and for these given, lengths r. Okay. So remember, technically angles are dimensionless, right? So I know sometimes we call them, we say angles have a unit of radians, or maybe they have a units of degrees, but in the grand scheme of things, we say that they're non-dimensional. Okay. And this is kind of where it comes from. So it's you can think of it as kind of the percentage of a circle or the segment of a circle that's subtended by an arc. Okay. So that's that's one way to look at the concept of an angle in two dimensions, right? So kind of relating it to a circle and saying that this angle represents that percentage of that circle. Okay. Now let's extend this idea to three dimensions. And so that instead of a circle in three dimensions, we're going to look at a sphere. Right. So in 3D. So for a sphere, okay, we can define a new type of angle called the solid angle. Okay. And so for a solid angle, we're going to use it in the same way that we do in two dimensions. So a solid angle will describe the segment of a sphere or the percentage of a sphere that's subtended by a certain area. Okay. Okay. All right, so it looks kind of like this. And so, if you have, a patch, right? So let's say that we have a patch, imagine a sphere, right? Actually, let me draw a sphere. Let me draw that first. Okay. Okay, so let's say we have our sphere here. We have our center of the sphere there. Okay. If I draw, if we draw out a patch, right, on the surface of this sphere, right? So let's say that we have a patch that's sitting on the surface, and we connect all corners of that patch to the middle. Okay. Right. So in a sense, we have kind of the same thing that we had with the arc right above. Okay. But if we wanted to describe the same thing, and it's a little bit hard to kind of tell here, right? But you can kind of see right at the origin down there, we have this kind of almost like you can think of like a shadow, right? That kind of plays the same role as the angle that we had in 2D, right? So this part of the sphere right here, this is what we call the solid angle. Okay. Let me draw another picture of the solid angle because I think that one's a little bit hard to see. But at least with this one, you can kind of see the whole sphere. Okay. So if I kind of blow this up, right? So I say that, we have kind of a patch that looks like this, right? And it's all originating from the center of the sphere here, right? Where once again, just like we had for the circle, each of these line segments here have the same length, right? And so since they go out to kind of the exterior of that sphere, we'll say they all have a length R, okay? And so this, it kind of looks like an area here, but the closest analogy I would say is to our concept of an angle, right? So this part of that shadow is called the solid angle. Right? Okay. So a solid angle, is nothing more than just kind of a three-dimensional generalization of our concept of an angle itself. Okay. Now, I will say this is, you know, not a traditional way to describe. So usually when you have, you know, a three-dimensional object like this, and you are using spherical coordinates, usually the way you describe this is with two separate angles, right? And so if you think of spherical coordinates, right? So the three variables in spherical coordinates is that you have your radius, you have the polar angle, and you have the azimuthal angle, okay? So this is a bit more traditional. So more traditional is to use kind of multiple angles to describe, you know, this this idea of a solid angle, right? But basically the solid angle takes up the job of both of these angles here, okay? They're not quite the same thing, but you know, they have the same idea of those two, okay? Okay, so as we, you know, as we kind of describe more of the geometry, we do more calculations with radiation, this concept of the solid angle will come up. And so, you know, I wanted to kind of take a minute to kind of really describe what it is, okay? Okay. So just like in two dimensions, a solid angle is dimensionless, and so it doesn't have any units. Okay. But just like our 2D angles, you know, solid angle does have like a pseudo unit that we use to describe it, just because it makes it easier to talk about it in the text. All right, so when you're talking about solid angles in the text, usually you refer to it by this term. Okay? And so the term for, it's kind of a silly name, but they're called steroradians. Okay? Or stradians, you can kind of say. Okay? Okay. And we have a formula for this as well. Okay. Okay. And so the formula that we're going to use to relate solid angle to other quantities is the following, right? And so what we say is that the solid angle, we give it the symbol omega. Okay. So omega here, this is a solid angle. Okay. This is equal to the area of the patch that we're looking at, divided by the distance from the patch to the center squared. Right. So this A here is the area of the patch. And this R here is the radius, but you know, we more specifically, we say the distance to the center. Okay. Okay. There's a lot of concepts in this equation right here that we'll go over in a second, but let me pause here just for a minute. Are there any questions on any of this so far? Okay. Okay, so let's look at this equation here and let's look at the different factors that can increase or decrease the solid angle. Okay. Okay. So let's look at the numerator first. So let's look at the area of the patch. What's up?
So for the spherical coordinates, I'm pretty sure I remember what they are, but could you just label them on the?
Oh, sure.
So I can see them again?
Yeah. That's a good idea. Okay, so our spherical coordinates, let me kind of do it here, just because I have a sphere conveniently drawn. Okay. So in spherical coordinates, you know, let's say that we are trying to describe, you know, the location of a point right here, right? Okay. So I think the easiest one to describe is the radius, right? So the R coordinate is just the distance from the center out to the object. Okay. Let me do the azimuthal angle first. Okay. So the azimuthal angle is the angle, the two-dimensional angle between, you know, this line R and this vertical axis here. Okay. And then the polar angle is the angle between, you know, that radius R and another axis within the sphere itself. Usually we take the horizontal x-axis. So it's a little bit hard to draw just because, you know, this is kind of in 3 dimensions here. But, you know, the this angle right here, if you kind of project this this down, right? That right there is the polar angle. Okay. Yeah, so we basically use these two, you know, two-dimensional angles to describe locations in 3 dimensions along with that radius. Yeah. Mm-hmm. Okay. All right, so let's go back to this equation here for the solid angle. Okay, so if we look at the numerator, okay, we see that if we increase the patch area, that's going to increase the solid angle. Okay. So that makes sense, right? And so if you have a sphere, right? If you have a much bigger patch, right? So let's say we have a patch that looks something like this, right? And we connect this all to the center, just like that, right? So a bigger patch is going to take up a much bigger percentage of the sphere, right? And so that makes sense. And that concept applies to 2 dimensions as well. So in 2 dimensions, you know, the bigger your arc, the much bigger percentage of the circle that you're going to take up, the bigger the angle it's going to be. Okay. So same thing here. So, you know, the bigger your patch, the bigger the solid angle. Okay. Okay. Now, the other factor here that affects solid angle, of course, is going to be your distance to the center. Right? Okay. So the closer you are to the center, okay. So in other words, as R decreases, this is also going to increase your solid angle. Okay. Right. And so if you took that patch and you brought it closer to the center, it's going to require a bigger solid angle to encompass kind of the whole thing. Okay. So actually there's a great analogy for this that I think, you know, everyone probably has, you know, some experience with to some degree. And if you're on Zoom, I apologize. So you're not going to be able to see this, you know, this riveting demonstration here. Okay. So if you think of a projector, right? So like the ones that we have here, you can think of solid angle as the shadow that's cast if you were to put your hand in front of the projector, right? So if I were to walk over here, right, and put my hand in front of the projector, you can see the shadow of my hand, right? Now, if I were to somehow grow my hand, so if I was like a Hulk or something, then the shadow would get bigger, right? Now, another way to increase the shadow is if I were to bring my hand closer to the projector, right? I'm not quite tall enough for this demonstration, but you know, you guys get the idea, right? Okay. So if you think of solid angle as this concept of a shadow, I think that kind of, you know, hopefully kind of ties everything together, right? And so these 2 factors here, you know, the size of your patch or the size of your object and the distance to the center or the distance to the emitting surface, both of those are going to affect your solid angle. Okay. Okay. So let's bring this back to radiation. Okay. And let's kind of tie this together with the, with what we know, or kind of what we started our discussion with, right? So today, we started our discussion with this idea that, when you have two objects, right, both objects are going to be emitting radiation, but not all of the radiation from one object is going to hit another one. Okay. Okay, so let's draw out that, let's apply this idea of solid angle to our radiation. Let's do. Okay, so let's draw an object here, and so just to make things simple, I'm going to make it a square. Okay, so let me draw a square here. Okay, so we'll call this square, we'll call it A1. Okay. So in this example here, we're going to assume that A1 is going to be emitting radiation in all directions. Okay. Right, so we know that A1 is going to be going every direction here. Okay. Now, for simplicity, we're only going to consider objects above A1. Okay. And so we're not going to consider objects below it. Okay. All right. Now, one way that we can kind of draw this geometrically is that, because we know that A1 is going to be emitting radiation in all directions equally, what we can do is we can draw a hemisphere around A1 that describes, locations where the radiation intensity is going to be the same. Okay. All right, so let me kind of show you what that means. So if we draw a hemisphere, so if I were to draw kind of a half sphere around this, okay, we kind of put a dome around A1. Okay. All right. And so we say that every point on this dome right here, at least on the dome part, is going to be an equal distance away. Right, so we say that the distance from the center of A1 to the edge of the hemisphere is R. Okay. If we draw a patch, right, so let's say that we draw a little patch here. Okay. So we'll call this patch dA. Okay. Right, and so actually let me do this. Let me draw the lines directly going to dA, just like that. Okay. Okay, so what we're interested in is, how much radiation from A1 is going to be hitting our little patch here, dA. Okay. All right, so that's what we want to determine, and that's what the solid angle is going to help us with. Okay. Okay. All right, so first thing that we're going to need to compute is we need to compute the area of this patch, right? Eventually, we're going to use this to compute solid angle. So let's do that first. Okay. It's kind of the weakness of iPad lecturing is that I can only show so much on the screen at once. Okay. I'll try to make it so that this sphere is always kind of in view. Okay. Okay, so we're going to describe the area of this patch, but we're going to do so in spherical coordinates. Okay. All right, so the area of this patch, we'll call it dA. is equal to R, which is the distance from the patch, from the corner of the patch to the center, times the polar angle d theta, okay? So this patch right here is going to subtend a certain polar angle d theta, okay? And then that's going to be multiplied by the length of that patch in the other direction. So we're assuming the patch is rectangular, but this rectangular patch is sitting on the surface of the sphere. Okay? So that's the product of r d theta and r sine theta d phi. Okay. All right. So if I were to draw that here, you know, this length right here, this would be r d theta, and this edge length of the patch here, this is r sine theta d phi. Okay. So we're just taking, you know, just the product of the two edge lengths. It's just that those two edge lengths are described in spherical coordinates. That's why they kind of have this kind of weird expression there. Okay. All right. So if we take this area, right, we can use this to compute the solid angle that's subtended by this patch. Okay. Now, I've been using that term subtended a lot today. Subtended just means that, you know, what angle is this creating, or, you know, how much shadow is this creating, right? So what is the solid angle that's being created by this patch existing, right? Well, let's use our formula, right? So we know that solid angle is equal to the area of the patch divided by r squared, okay? So we have an expression for the area of our patch, which is dA, okay? So we're just going to divide that by r squared. And conveniently, you can see here that all of the r's are going to cancel out, right? So this r squared in the denominator is going to cancel out with these r's up here. Okay? And so the solid angle that's subtended by this patch is sine theta d theta d phi. Okay. Okay, good. All right, so it's a good start. So we have our patch. We want to find out how much radiation is hitting this patch, and we've already computed the solid angle that we are going to use. Okay. Any questions on this so far? Okay, good. All right, so that's a good start. Okay. Another factor that we have to consider is that, you know, if we're sitting on the surface of A1, you know, how much of this patch are we going to be able to see? Because remember, you know, a big part of radiations is optics. Now, that's not optics in the way that, you know, is used in, you know, in the media today, but literally just, you know, how things are seen. Okay. Okay, let me give you kind of two examples here. Right? Okay, so we know our surface A1, right, is a surface that's flat, and, you know, for, you know, just for the sake of interpretation, we can assume it's flat on a tabletop, right? Okay. And so if you consider, you know, this surface to have, you know, like an eye, right? Okay. If we had another surface up here, right? So let's say we had a second surface up here, we'll call this A2, right? Right. And our eye is fixed to be, you know, in the direction of A1. So in this case, looking directly up from the tabletop, right? What we can say is that, you know, from the perspective of A1, the entire surface of A2 is visible from A1 because it's there. These two surfaces are essentially facing each other. Okay. All right, so since these two surfaces, you know, they're basically facing each other head on, you know, these two surfaces can perfectly see each other. Okay. Okay, now let's look at another surface. So let's look at another surface here, A3. Okay. Now A3 is off to the side. Okay. Now, if we look at the same eyeball, right? So if we look at the same eyeball that's facing in the direction of A1, right? A3 is not fully visible between, you know, A1 from the perspective of A1. Okay. Okay. Now, both A2 and A3, you know, they may be the same distance from A1, right? So let's say that they both have the same value of R. Okay. Right? But even at the same distance, you know, depending on where you're standing or where the patch is relative to the orientation of the original surface, right? It's going to change how much radiation that you receive, right? So A3, what we say in this case, A3 has a smaller effective area for radiation because it's standing off to the side. You know, the two surfaces are not perfectly aligned with each other. Okay. Right. So another way that you can say that, another way that you can see this is that because it's off to the side, right? And A1 is going to be you know, most of its radiation is going to be pointed, you know, perpendicular to that surface, right? There is going to be some radiation that comes off to the side, but it's not going to be nearly as much, right? And so this factor, we have to account for that in our calculations. Okay. Okay. So we can account for this. And so actually, if we, you know, if we draw a line that's perpendicular to our original surface, right? So this line right here is perpendicular, right? If we draw an angle, a 2D angle, let me use different colors here to be a bit more clear. Okay. Right. And so if we draw kind of a line that goes directly from A1 to our side surface A3, right? And we can call this we can give this an angle. And let me use a different symbol here just because, you know, we've been doing angles out the wazoo today, right? So we'll call this angle gamma, okay? Right. So this angle right here, this angle gamma right here, this is going to be a you can call it a correction factor that's given due to these surfaces not being completely aligned with each other, okay? All right, so this is our formula for effective angle or effective area, excuse me. Okay, so our effective area in this case, we'll call it dA, is equal to cosine of that angle gamma, okay, multiplied by the solid angle. All right, and so if we plug in our expression for the solid angle, this gives us cosine gamma sine theta d theta d phi. Okay. Okay. I know it's a lot of geometry today, a lot of spherical coordinates, but there is one example that we're going to do at the end. I think hopefully we'll kind of tie everything. I think this is one of those things that once you start to see some numbers, once you start to see some situations, it'll start to make a bit more sense. All right, any questions on this so far? Yeah.
The drawing that you gave us, can I see the camera?
Yeah. Mm-hmm.
So what is that once again?
So this gamma angle is just it's an orientation angle. So it's the fact that this patch is not going to be facing, if the patch is not fully kind of straight on facing the object, then there has to be a correction factor because it's not going to experience the full radiation. Yeah. Mm-hmm. Okay, good. All right, so we're just about ready to compute things, because now that we have the effective area, right? This effective area you can consider to be how much of the radiation that this second object is going to experience. Okay, so let's just kind of bring it all back. Okay. Okay. Okay, so if we go back to the original surface A1, right? Let's start by computing the total amount of heat transfer that A1 is emitting. Okay. Okay. So if we compute Q is equal to the product of E. Remember, E is the spectral heat flux, or the total emissive power coming from the object. Let's see. Right, so that E there, that was the product of emissivity, or Boltzmann constant, and the surface temperature. Okay. Right, and so if we want to get this in the units of watts, then to do that, we're just going to multiply by the area A1. Okay. Okay. And so what we said is that this heat transfer is going to be spread equally within that hemisphere that we drew. Okay. Okay. And based on our discussion today, that based on where the hemisphere is, or basically based on the radius of the hemisphere, that's going to affect how much heat transfer that you're going to occur, right? The further away you are from the object, the less heat transfer that you're going to experience, right? Okay. And that was given to us from the solid angle, right? So the bigger the radius, the less solid angle that you'll have, the less heat transfer that you will, that you'll experience, okay? Okay, so let's define a new quantity, right? A quantity that is, independent of the distance, right? Okay, so if we define a new quantity called intensity, okay, so if we define the radiation intensity to be just the division of our total emissive power by the total area or surface area of the hemisphere, okay? So I here is going to be intensity. This is equal to total emissive power E divided by area of the hemisphere. Okay. Now this is total area of the entire hemisphere at a certain distance r. Okay. Okay. Right. So intensity, intensity describes, how much of the radiation that you're going to be experiencing, in terms of, I think I like to think of intensity as the amount of radiation beams that gets intercepted by a certain distance. Okay. And so if you consider radiation to be, a bunch of laser beams coming off from an object at a given time, intensity tells you, how many of the laser beams that you are intercepting by placing your hand above that object, okay? I know that was kind of very Star Wars-y type of explanation, but, once you see the example, I think it'll make a bit sense, okay? But we like intensity because it is independent of distance, right? And so, whether you are really, really close to the object or really, really far, intensity kind of stays the same. It's a property of the object emitting itself, okay? All right, so if we solve this quantity here for E, right, we can say that E is equal to I times area of the hemisphere. Okay. All right. And so if we plug this back in, right, so right above this, we have an expression for Q, the heat transfer, right? So we say that Q is equal to E times A1, okay? We can say that Q is equal to the intensity of the radiation multiplied by A1 multiplied by area of the hemisphere, okay? Right. Okay. So why would we do this, right? Okay. Now, the reason we did this is because this area of the hemisphere, right? Or the reason we put this formula in this form is that we can easily modify this equation depending on the size of our patch, okay? And so, this equation right here is, relevant for the entire hemisphere, right? But, most of the time, you only have an object that takes up just a small slice of that hemisphere. Okay? Right, so if instead we replace this, okay, Instead of the area of the entire hemisphere, we replace this with just the area of the object that we're considering. We can compute the amount of radiation that goes from one object to another. All right, so actually, let me give you the most common form for this. The most common form for this is going to use the solid angle, right? So this is kind of go all the way back to kind of our expression above. Okay. Okay, so if we express this with solid angle, we finally get the equation that we're going to use in an example, right? Where our equation here is Q, right? So this is the radiation that comes off of one object and is caught by another one. Okay, so this Q is equal to I. Okay, so remember, I is the intensity of the original emitting surface. Okay, we're going to multiply that by A1. So A1 here is the surface area of our original radiating surface. Okay. And then we're going to multiply this by the solid angle of the receiving surface. Okay, so this is omega. Okay, so I'll just call it the receiver, right? So the receiver is going to subtend a certain solid angle relative to the original object, right? So that's what we're going to compute. And then we have to multiply that by our correction factor, right? So that's, remember, our effective area depends on whether our receiving surface is aligned with our original one. Okay? So we're going to multiply this by cosine of gamma. Okay? So the cosine of gamma, this is our correction factor. All right, so relatively simple formula. You're going to see that the example that we're going to do is fairly short, but you know there was a lot of context and a lot of buildup for this formula here. Okay. Okay. All right. So thankfully, you know, after all of that discussion, the example is, you know, fairly straightforward, I would say. It's just kind of applying this this formula here and applying the geometry, but you know, obviously there was a lot that we had to describe to get up to this point. Any questions on this before we jump into an example? Okay, let's do one quick example today, and then we'll wrap it up for today. Okay. All right, so let's say that we have a small surface that's emitting radiation. Right, so the properties of the surface, we have its surface area, A1. So A1, we're going to assume is 0.001 meters square. Okay. We also know its intensity. Okay. So the intensity of the object emitting is 7,000 watts per meter square. Okay. Pretty high, all things considered, but you know, we need the numbers to be high for this for this example here. Okay. We're going to consider two different receiving surfaces. Okay. So our two other surfaces, we'll call it A2 and A3. Okay. And what's going to be different about these two are they're going to be their relative orientations. Okay. Okay, so let's draw it out. So let's start with A1. Okay. So our A1 surface is down here. Okay. We're going to consider A2. A2 is going to be right facing A1, okay, just like we had above. And then A3 is going to be off to the side at a correction angle of 45 degrees. Okay, so A2 right here, this is going to be, you know, going to be directly facing A1. Okay. And then A3 is going to be off to the side by an amount of 45 degrees. Okay. Now both surfaces are the same distance. So we're going to say that A2 is 0.5 meters away from A1. Same thing for A3. Okay, so A3 is going to be half a meter away from A1. Okay. And both of these A2 and A3 have the same area as A1. So A2 here is going to be 0.001 meter square. A3 is 0.001 meter square. Okay. All right. So in this simple example here, we're gonna compute a couple things. Okay, so the first thing we're going to compute is we're going to compute the solid angle that's subtended by both of these surfaces. Okay. Just because, you know, you guys probably have never computed solid angle before, so let's do that together. Okay. Okay, and then two, we're to compute the rate at which radiation is being received or intercepted by A2 and A3. Okay. All right, any questions on this so far? Okay, good. Okay, so let's just go ahead and chug through the problem here. Okay, so let's do part one first. Okay. Now, A2 and A3, the solid angle subtended by these two surfaces is actually going to be the same because they both have the same area and they both are the same distance away from A1. Okay. So the solid angle for both, let's plug in our formula for solid angle. So solid angle, remember, is area of the receiving surface divided by the distance squared. Okay. So both A2 and A3 have the same area, which is 0.001 meters square. Okay. And they both have the same distance, right? So both distances are half a meter. Okay. So we're going to divide there by 0.5 meters square, right? So if we do this math right here, pretty straightforward. And so what we're going to get here is 0.004. Okay. And remember, solid angle, technically unitless, but just so that people know we're talking about solid angle, we'll give it our pseudo unit. And so our pseudo unit here is steradians or steradians. I don't know why I think that's such a funny word, steradians. Okay. All right, pretty straightforward there. Okay. All right, part 2. All right, so now that we know the solid angle for both A2 and A3, we are ready to compute the radiation heat transfer from A1 to A2 and A3. Okay. All right, so for this one, we are going to use our formula that we just finished with right before this example. Okay, so you have Q is equal to intensity times our original area times solid angle times cosine of our correction angle here. Okay, so if Q is equal to I multiplied by A1 times omega cosine of gamma. Okay. All right, so all we got to do is just plug in for all of these. So our intensity here is 7,000 watts per meter square. Okay. So this is for A2. Okay. So our original area here, our original area for A1 is 0.001 meters square. Okay. Solid angle we just computed. We're just going to pop that down here. So 0.004 steradians. Okay. And then we're going to multiply by cosine of the correction factor. Now, A2 is facing A1 directly. So what we can say here is that our correction factor, or correction angle, is going to be 0 degrees. And this is since A2 and A1 are perfectly facing each other. All right, so we plug everything in here. We punch it into a calculator. We get 0.0028 watts. Okay. Okay, so that's the amount of heat transfer that A2 is receiving from A1. Okay, so let's do the same thing for A3. Okay. So A3 is going to be the same. Okay. So I'm not gonna write down all those numbers again. The only difference for A3 is that we have to account for the fact that A3 and A1, A3 is a little bit off to the side. Okay. Okay. And so we're going to correct for that by multiplying by cosine of 45 degrees. Okay. So this cosine comes from that last factor, which is this factor down right here. Okay. Okay, so if we plug everything in for that, what we get is something slightly less as expected. Okay. So we get 0.00198 watts. All right. All right, so pretty straightforward. So once you get the solid angle for these problems, then the rest is kind of plugging in from there. Any final questions before we wrap it up for today? Yeah. Yeah.
I know all the areas the same, but is it for A1 or A?
Good question. Yeah, so this area here for the solid angle, that's the receiving area. So in this case, this would be A2 and A3. Yeah, good question.
So if we had a separate area for A2 and A3.
Exactly, yeah. So A2 in this case would be like 0.002, then it would have a separate solid angle than A3. Would be 0.002. Good question. All right, that's all. Question, yes. Exactly, yeah, so in this case, you're gonna draw a line. Based off that. All right, thanks, everyone. I will see you guys on Thursday. I'll have your exams by Thursday too. Yeah.
You notice how much we were all sniffling?
Wait, what?
You notice how much we were all sniffling the whole class?
A little bit, yeah.
Trying to figure out if he noticed.
Oh, I'm kind of sniffling a little bit too.
We weren't
My-
like doing it on purpose,
It's
right?
just rude.
This room was just like.
Oh, yeah. It's a little bit kind of.
Moldy.
A couple times, like, I'd come in here for class.
Yeah.
You could only find, and all of a sudden sniffling like crazy. Class
I
not
left,
writing
I
it,
left the
like,
room 3 times before I had.
Oh, yeah, that I know. I mean, during the exam, people were like stepping out to like,
Yeah.
and stuff. Yeah, I don't know what it is with this room. Maybe they gotta clean the filters on the fan. That might.
But that, I don't know. Floor, it's probably super dusty.
Maybe, yeah. That's true.
Yeah, we're all dusty. That's like, what's that character from Charlie Brown that has like the.
Oh, yeah.
Yeah,
Yeah.
What's that guy's name?